Hash tables. Imagine going to a library where the books aren't sorted like what you see in this picture, where each time a book gets returned, instead of the librarian taking that book to an assigned location, it simply tosses it into a pile. Right? Obviously, searching for books in this kind of library would take a long time because the book could literally be anywhere in the building. You wouldn't know where to start, which, as you know, is why libraries organize their books. First, they organize it by genre. Then within each genre section, they organize it by author. Then within each author section, they organize it by the call number. All this serves to make searching for books as fast as possible. Hash tables, as you will see, operate in a similar manner. Each Java object you create in a program gets assigned a number called a hash code, similar to how each student who enters the district gets assigned an ID number. Whenever you insert an object into a hash table, its hash code value gets plugged into a math formula called the hash function. This determines the assigned location for that specific object. For example, suppose I have a hash table that uses an array of size 10 to store its values. Then suppose these are the hash codes, the values I want inserted into this hash table, and this is the hash function I'm going to use to store them, where the function is simply the hash code modulo n, where mod is simply short for the modulo operator. Right? Let's do that. First value 2, 2 modulo 10 simply equals 2, so that's where 2 gets stored. Next, you have 14. 14 modulo 10 equals 4, thus that's where 14 gets stored. Next, 6. 6 modulo 10 equals 6, so that's where 6 gets stored. Then 38. 38 modulo 10 equals 8, thus that's where 38 gets stored. Then lastly, 20 modulo 10 equals 0, thus that's where 20 gets stored. Though we didn't encounter any problems in that example, a potential problem you may have noticed while we're doing it is that there are a lot of different values that could potentially map to the same location. For example, any number ending in a 0 would have mapped to location 0. Any number ending in a 1 would have mapped to location 1, and any number ending in a 2 would have mapped to location 2, so on and so forth. Thus, had I continued the last example by trying to insert 30, for instance, I would have ran into a roadblock because the location that 30 is supposed to be stored at is already occupied. Anytime you attempt to insert a number at a location that's already occupied, we call that a collision. And there are three types of ways a hash table can handle a collision. The first way is the chaining method. With the chaining method, each position in the array maps to a linked list, storing all the values that map to that location. So, suppose I'm using an array of size 5. These are the hash code values I want inserted to the table, and my mod function is simply the hash code modulo 5. First number is 1. 1 would get stored at location 1. Then we have 2. 2 would get stored at location 2. Okay. Plug in 4. 4 would get stored at location 4. Then we have 6. 6 would get stored at location 1. So 6 would get added to that linked list. Next we have 7. 7 would go to location 2. So 7 would get added to that linked list. Then we have 8. 8 maps to location 3. That's where we put 8. 10 would map to location 0. 11 would map to location 1. 12 would map to location 2. And 15 would map to location 0. The other approach is the linear probing method. The way linear probing works is you take the hash code, determine its location, then check to see if it's occupied. If it's not, then place the value there. If it is occupied, then probe the next slot to the right. If it's not occupied, then place the value there. If it is occupied, then probe the next slot to the right, so on and so forth. So for this example, let's start with the number 1. When we plug the 1 into the hash function, we see it maps to location 1. We check to see if it's occupied. It's not, so we put the 1 there. Next, number 6. Number 6 maps to location 1. We check to see if it's occupied. We see that it is, so we check the next slot. This one is not occupied, so 6 goes there. Next, 4. 4 maps to location 4. Let's check to see if it's occupied. It's not, so 4 goes here. Next, 0. 0 maps to location 0. Check to see if it's occupied. It's not, so 0 goes there. Next, the number 9. 9 maps to location 4. 4 is occupied. So let's wrap around back to 0, occupied, then to 1, occupied, occupied, unoccupied. So 9 would go here. The last technique we're going to discuss is the double hashing method. And the reason it's called double hashing is because we use 2 hash functions to determine the right location for a value. Here's what I mean. Suppose I start at 15. I plug 15 into the first hash function. I get the number 5. I check to see that it's occupied. It's not, so 15 would go here. Next number, 8. 8, when plugged into the first hash function, gives us 8. We check to see that it's occupied. It's not, so 8 would go there. Next, 5. 5, when plugged into the first hash function, maps to location 5. We see that it is occupied. However, rather than simply check one spot to the right, I'm going to plug 5 into the second hash function to determine how many spots to the right to go. So when I plug 5 into the second hash function, I get 2. So that means we're going to check 2 spots to the right. 7 is empty, it's unoccupied, so 5 would go here. Next, 11, when plugged into the first hash function, maps to location 1. 1 is unoccupied, so 11 goes here. Next, 18 maps to location 8. 8 is occupied, so we're going to plug 18 into the second hash function. We get 3, which means we're going to go 3 spots to the right. 1 is also occupied, so we go 3 spots to the right again. 4 is unoccupied, so 18 goes here. Next, 1. 1 maps to location 1. However, 1 is occupied, so we're going to plug 1 into the second hash function. We get 6, so we're going to check 6 spots to the right. 7 is also occupied, so we go 6 spots to the right again. 3 is unoccupied, so 1 goes here. Next, 13. 13 maps to location 3. However, 3 is occupied, so we're going to plug 13 in to the second hash function. We get 1, so we're going to check 1 spot to the right. Location 4 is also occupied, so we go to the right again. Location 5 is occupied. Location 6 is not, thus 13 goes here. And then last but not least, 25 maps to location 5. However, 5 is occupied, so we plug 25 into the second hash function. We get 3, so we're going to go 3 spots to the right. 8 is occupied, go 3 spots to the right again. 1 is also occupied, 3 spots to the right. Occupied, 3 to the right. Occupied, 3 to the right. 0, location 0 is unoccupied, thus 25 would go here.